In the last few lectures, we were looking at solving problems in an infinite domain using similarity solutions. In the first instance, it was diffusion into an infinite medium, where you had the temperature T is equal to T infinity far away, and the temperature is at the surface is instantaneously increased to a higher value, T is equal to T naught, okay. And at T is equal to 0, T is equal to T infinity for z greater than 0, where z is the distance from this surface, okay. Z is the distance from this surface, okay. And we saw how the temperature varies with time, okay. Initially it is T 0 here and T infinity here, and as time progresses the temperature evolves in such a way that the temperature at the surface is the same, the temperature at infinity is the same, but the penetration depth of that temperature changes, okay. We had defined T star is equal to T minus T infinity by T naught minus T infinity. This was equal to 1 minus the error function of z by 4 alpha T, okay, where alpha was the thermal diffusion coefficient. No, I am sorry, it should be 2. Z by 2 root alpha T, where alpha is the thermal diffusion coefficient, okay. And the other problem that we had considered was where you had a pulse injection at the origin, okay, at z is equal to 0, and there was diffusion with time, okay. And the initial condition in this case was that the concentration is equal to the mass injected per unit area, okay, in one dimension, the mass injected per unit area times delta of z, okay, and the diffusion equation was the same, and we got a solution, a similarity solution using the same similarity variable z by root dt now, okay, whereas in this case the similarity variable was z by root alpha t. And the solution that we got was that C is equal to m by 2 root alpha t e power minus z square by 4 alpha t. Okay. In both of these instances, the diffusion was into an infinite domain. There was no length scale, and therefore, we could get only one way of scaling length, and that was by a combination of the diffusivity and time. Okay, and on that basis we were able to derive a similarity solution, okay, in both of these cases. The similarity transform can also be used when you have a finite but time dependent length scale, okay, in such a way that the length scale has a specific dependence on time that is consistent with a balance condition. Okay. So, let me illustrate that in one dimension for a specific problem. Okay. Let us say that I have some block, okay, that is melting, okay, as a function of time. Okay. So, initially what will happen is that this block is at some temperature T is equal to T naught. Okay. I am sorry, let us assume that the block temperature is maintained at the melting temperature, okay, T is equal to Tm. Okay. And at time t is equal to 0, you bring it into contact with a surface at higher temperature T is equal to T naught, where T naught is greater than Tm. Okay. So, since there is a temperature difference between the surface and the block, there is going to be heat transfer to the block, and that heat transferred is going to go into the latent heat of melting. So, therefore, you are going to have some zone here which is a molten zone. Okay. some zone here which is a molten zone, and there is going to be a heat flux that is going into the molten zone. This is Qz, okay, the heat flux that is going into the molten zone because of the temperature gradient at that surface, okay, because of the temperature gradient at that surface. Okay. So, if I plot the temperature profile in this region, okay, I take a coordinate z, and let us assume that the total thickness of this region is h, which is a function of time, because as the melting proceeds, the thickness of the zone increases. Okay. So, let us say that I have a thickness h which is a function of time. This is z is equal to 0, this is z is equal to h, which is a function of time. Okay. And as the melting proceeds, this h increases with time. Okay. If I plot the temperature here, okay, as a function of z, if I plot the temperature, okay, it is equal to T naught here, okay, and it has to be equal to the melting temperature here. So, it has to decrease in some way from T naught to Tm. Okay. The temperature field has to decrease from T naught to Tm at the surface, because at the surface it has to be at the melting temperature, whereas on top it is at a higher temperature. Okay. And the heat that is transferred, okay, is related to the amount that is melted per unit time. Okay. The heat flux times a time interval delta T has to be equal to the amount that is melted, okay, in that time delta T. Okay. So, let us take a material with specific heat Cp, thermal conductivity K, okay, density rho, and latent heat, I will call it as lambda. Latent heat is the heat required per unit mass for melting. Okay. The heat required per unit mass for melting is what is called the latent heat. Okay. First, we will solve the heat diffusion equation, and then look at the condition required for melting, and then see under what conditions we can get a similarity solution. Okay. So, that is the procedure that we will use here. So, scale, okay, T star is equal to T minus Tm by T naught minus Tm. Okay. T star is equal to T minus Tm by T naught minus Tm, and this z I will scale it by the height. Okay. So, that here z star is equal to 0, here z star is equal to 1. Okay. At z is equal to h, z star is 1, at z is equal to 0, z star is equal to 0. And at z is equal to 0, t is equal to T naught. Okay. At z is equal to 0, t is equal to T naught, therefore, okay, T star is equal to 1, and at z is equal to h, t is equal to Tm. So, t minus Tm will be 0, and T star is equal to 0. Okay. So, the boundary conditions in terms of this z coordinate are at z star is equal to 0, T star is equal to 1, and at z star is equal to 1, T star is equal to 0. Okay. So, those are the boundary conditions. The conservation equation, the diffusion equation, partial T by partial T is equal to alpha times partial square T by partial z square. Okay. That is the conservation equation, and we have to see whether this transform, okay, a similarity solution can be used only if this transform results in an equation which depends only on z star and not individually on z, t or h. Okay. H is a function of t, okay, in this particular case. So, this transform gives you a solution only if the final equation depends only on z star and does not depend individually on z and t. Okay. So, how do I convert the derivatives from z to z star? Okay, by using chain rule for differentiation. Okay, partial. Okay, so since the temperature is a linear function of T star is a linear function of T, this equation can be easily transformed as partial T star and partial T star here, okay, because it is a linear function. So, I will just get a factor of T naught minus T m on both sides, which will cancel. Okay, so, this is expressed in terms of the scale temperature. Now, how do I get the equation in terms of the similarity variable z star? Okay, by using chain rule for differentiation. Okay. Partial T star by partial z is equal to partial the total derivative here, because we are assuming that T depends on z and T only through its depends on z star. Okay, that is the reason for the total derivative here. Okay. And partial z star by partial z is 1 over h. Just using chain rule for differentiation. Okay. The second derivative is obtained quite easily. Okay, d square t by dz square is equal to, okay, when I take the derivative, I will just get a second factor of h in the denominator. Okay. So, I will just get 1 over h square d square t star by dz star square. Okay. When I take a second derivative, I will just get another factor of h in the denominator. Okay. Now, what about the derivative with respect to time? Okay, the time derivative. Okay. Partial t by partial t is equal to partial z star partial t let me just write it on the left so that I can do the calculation. Okay. This is equal to minus z by h of t the whole square dh by dt dt by dz. Using chain rule for differentiation, derivative of 1 over h is minus 1 over h square times dh by dt. Okay. And since z by h is z star, I can write this as minus z star by h dh by dt d of temperature with respect to z star. So, I substitute this into the conservation equation. I substitute this into the conservation equation and I will get minus z by h dh by dt dt by dz is equal to alpha by h square d square t and I multiply throughout by h square by alpha, so that the coefficient on the right side becomes 1 and I will get minus, okay, h by alpha dh by dt into z star And obviously a similarity solution can be used only if this is a constant, okay. Can be used only if this is a constant, okay. Otherwise we cannot get a similarity solution, okay. Note that the boundary conditions are of course not dependent upon z or t. The boundary conditions are at z star is equal to 0, t star equal to 1, and at z star equals 1, t star equals 0. So, the boundary conditions do not depend upon explicitly on either time or z, but this term here, this term on the left does explicitly depend on time, okay. Only if this term is a constant can we use a similarity solution. How do we find what is this term? Okay. So, the way it is done is to do a balance, okay, do a balance where I consider that there is an amount that is melted, okay. Delta H is the amount that is melted, let us say in a time delta t, okay. Let us say that I have melted a certain amount delta H in a time delta t when the heat flux is Qz, okay. So, what I require is that the total heat transferred in the time delta t has got to be equal to the latent heat times the mass of material, okay. The total heat that is transferred due to conduction within a time delta t has to be equal to the latent heat times the total amount of material that is transferred, okay. That is, total heat transferred in a time delta t is the heat flux, heat transferred per unit area per unit time at z is equal to h, okay. At that surface z is equal to h, the total heat that is transferred, the heat transferred per unit area per unit time times the area into time, okay. The total heat that is transferred per unit area per unit time multiplied by the area multiplied by time has got to be equal to the mass that is melted, okay. The mass that is melted is the density times the volume, okay. The mass that is melted is going to be the density times the volume, okay. Volume is A times delta H, okay. Okay. That is the mass that is melted times the latent heat. Latent heat is heat required per unit mass multiplied by the mass that is melted gives you the total heat that is transferred. Okay. So, this is the condition. Note that the flux is at a specific value of z is equal to h. Okay. Note that the flux is at a specific value of z is equal to h. Okay. Now, Qz, okay, I can substitute Qz at z is equal to h is equal to minus k dt by dz. Okay. This is actually a partial derivative. Okay. Substitute t in terms of t star, substitute z in terms of h. Okay. So, I will get minus k into t naught minus t m by h dt star by dz star at z star is equal to 1. Okay. That is the total heat flux. Okay. That is the total heat flux. Okay. The area cancels out on both sides of this equation. The area cancels out on both sides of this equation, and therefore, I have minus k into t naught minus t m by h dt by dz at z is equal to 1, okay, is equal to rho lambda, okay, delta h divided by delta t. Okay. I have cancelled out a on both sides, divided both sides by delta t. Okay. And if I take the limit as delta h and delta t go to 0, okay, this gives me an expression for dh by dt. Okay. is equal to minus k T naught minus Tm, okay, by rho lambda h, okay, dt by dz. Okay. That gives me an expression for dH by dt. Okay. Note that dt by dz at z is equal to 1 is a negative number. Okay. Note that dt by dz at z is equal to 1 is a negative number. Okay. The reason is because the temperature decreases as z increases. I had said that the temperature is higher at this surface and lower at the interface, because that temperature difference has to result in a transfer of heat flux to the interface. So, therefore, the temperature gradient is negative, dt by dz is negative, because temperature has to decrease as z increases. Okay. So, therefore, dH by dt is a positive number. Okay. Therefore, dH by dt is a positive number, and if I multiply throughout by h, I will get h dH by dt, okay, is equal to minus k to T naught minus Tm by rho lambda dt star by dz star at z star is equal to 1. Okay. Note that this derivative is at the interface, okay, at the interface between the molten and the solid material. Okay. So, it has a fixed value. Okay. If T star is a unique function of z star, then dt by dz has to be equal to a fixed value at that interface. We do not yet know what that value is, okay, but it is a constant. It is not a function of z or z star. Okay. So, this expression for dH by dt I can substitute in here, okay, to get an expression of the form minus p z star dt by dz is equal to d square t star by dz square, okay, where p is equal to minus k into T naught minus Tm by rho lambda alpha, okay, this factor of alpha in the denominator, okay, this factor of alpha in the denominator times dt by dz at z is equal to 1, okay, times dt by dz at z is equal to 1. P is a positive number because I said dt by dz is negative at the interface, temperature decreases as z goes to 1. Okay. And now, because dt by dz is a constant, if t is only a function of z, the value of the derivative at z is equal to 1 is a constant, okay, and all other terms in this expression are also constants. Okay. Therefore, p is a constant and we can solve this. A similarity solution can be applied in this case, okay, because p is a constant. Okay. We do not yet know what that constant is. That has to be determined self consistently from the condition that p is given by this value. Okay. We can simplify this a little bit by writing for alpha is equal to k by rho Cp. Okay. If I write alpha is equal to k by rho Cp, then rho and the thermal conductivity will cancel, and I will get minus Cp into T naught minus Tm by lambda dt by dz. Okay. And note that Cp into T naught minus Tm and lambda both have the same dimension of energy per unit mass, because mCp delta T is an energy and therefore, Cp times delta T is energy per unit mass. Lambda is also an energy per unit mass. The numerator is the energy that is required to increase the temperature of the molten material from T naught to Tm. Denominator is the energy required for melting. Okay. Okay. So, therefore, the numerator and denominator both have the same dimension of as energy, and this thing is what is called as the Jacob number. Okay. This thing is referred to as the Jacob number, okay, J A is equal to C P into T naught minus T m by lambda. Okay, that is a dimensionless group. Okay. So, I can write this as minus J A times d t star by d z star at z star is equal to 1. Okay. So, that is the final expression. Yeah. So, I have to solve this equation. Where P is as yet unknown, but which has to satisfy the consistency condition that P is equal to minus the Jacob number, that is a specified number, times dt by dz at z star is equal to 1. Okay. That is the consistency condition which emerges from the fact that the total amount of heat that is transferred to the surface has to be equal to the latent heat for the amount of material that is melted. Okay. This condition here, okay, that the heat flux times the delta T has to be equal to the total amount of mass that is melted times the latent heat. Okay. So, that consistency condition has to be used in order to determine what is this value of P. So, beforehand we do not know what is the value of P, but we have to determine that from the solution, and subject to the boundary conditions T star is equal to 0 at z star is equal to 1, T star is equal to 1 at z star is equal to 0. Okay. So, those are the equations and the boundary conditions that have to be solved. Okay. Okay, how do we solve this equation? Okay. If you recall, when we had discussed conduction from a surface into an infinite medium, I had briefly discussed for you the error function. Okay. The error function is, the equation for the error function is minus 2 z star df by dz star is equal to d square f by dz star square. Okay. And the solution for this was f is equal to 2 by root pi e power minus z star square. That was one solution. The other one was of course a constant. Okay. This factor of 2 by square root of pi, basically because this is normalized in the sense that integral 0 to infinity dz star f has to be equal to 1. Okay. From that normalization condition we got that constant in front. Okay. I am sorry. Okay. This is the error function. Okay. This is equal to error function of z star. Okay. This satisfies the normalization condition. If you recall that, in case you do not recall it, kindly go back and revise that error function solution. And we also had the derivative. Okay. Yeah. Okay. Okay. And we had the functional form, it went to 1 far away, okay, and the slope at this point was 2 by root pi. Okay. Okay, we had discussed this earlier. In this case, instead of 2 we have this parameter p. Okay. Instead of 2 we have this parameter p. So, we just have to modify that solution a little bit in order to get this parameter p instead of the factor 2 in the equation for the error function. Okay. So, we will continue this in the next lecture, and I will see you